So hello everyone. So today we are going to be study about the concept to how to read the reference manual for your microcontroller. So today I just taken one microcontroller reference manual. So based on that you can able to read it and you are going to be implemented for your microcontrollers. Okay. So it is definitely going to be help you. So first of all, if you are going to be open up one reference manual, for example, I've just opened. This is the reference manual I just provided to you. Okay. So this complete thing, so what they have been already given in this reference manual. So first of all, either this is a in this it is having a like introduction. Okay, they have been given the introduction about this what microcontroller you are going to be read and what is actually present inside this and what are the processor name and so something which have been given. So these concepts and all you might be already read it in the reference manual. So the related uh, documents, so which you already read it on the STM32 the data sheet. So that's what I'm telling you. Both the things are very important. Okay. So this is the introduction part, and this is the content what is actually inside this book. Okay, so I'm going to be re-share it again, so it might be help you. So the thing is, first of all, in this contents, they have been given the abbreviations and they have been given a lot of stuff. So what are the index part, which is considered as an index? So what is actually present inside this complete reference manual? So first of all, the documentation conversion. So this means what they have been given is in this first page, list of abbreviations for your register. So like abbreviations means, so you might be having if you're a beginner, so I don't know how to read it. So I don't know some words, so they have been given. So complete abbreviations has been given at the first introduction. Okay. So in this groceries, yeah. In this one, so the list of abbreviations has been given. So sometimes they have been given RWR, so WRC. So what does actually mean? Okay, so you can able to understand what is mean the toggle reserve. Okay, software can only toggle this bit by writing one, writing zero as not. So you can able to understand the meanings of abbreviation. Okay, so what is mean by read and write? Okay, what is mean by read? So everything with the full form you can able to understand. The glossaries means you can able to understand what is the purpose of each and everything. Okay, so word means what is what? The data and instruction of 32 bit length. So whatever the data which is in 32 bit length, we call it as a word. Okay, and half word means whatever the data which is in the 16-bit length, it is going to be called as a half word. Byte means it is one byte is 8-bit length, right? So these are the data so you can able to understand. So double word means you can, so you can also implement it in your programming. Okay, so you have to be understand those concepts. What is word? It is about 32 bit length. Half word means 16-bit length. A byte means 8 bits. A half word means it is a 64 bits. Okay, sorry, double words means it's a 64 bytes. And what is the meaning of IAP? It's a application programming. So ability to reprogram the flash memory. So whenever you just seeing this AAP, it is a full form of you can able to reprogramming your flash memory. Now, what is meant by ICP? So it is an in-circuit programming. So ability to program the flash. It is a reprogram. It can able to program your flash memory using any JTAG protocols and serial wire debugger. So this is commonly going to be called as an in-circuit program. Okay, so normally we are using an STM32F411RE microcontroller, this serial wire debugger. So while we are doing this applications, okay, like while you're going to be uploading the programs code, so this is we are using serial wire debugger. So all we are going to be called it as. So for all those stuff, so what is meant by I code? So the bus connects the instruction bus of the CPU code to flash instructions of the peripheral. So it is actually the instruction going to be bringing through this bus. B code means it is bringing a data. Okay, it is actually going to be bringing it. So likewise, what is meant by AHP? So advanced high performance CPU. So here we have been using what is CPU. So refers to Cortex M4. We are going to be called it as CPU. Along with that, we are having FP. So it is a floating point. So you can able to get the lot of abbreviations. Okay, you can get the abbreviations as well as the glossaries of words which have been used in this reference manual. Okay, so you can also see this one. That is the first page they have been given. In this documentations conversions, they have been given the abbreviations, glossaries, and peripherals. You can, while you are going to read that, you can easily understand the concepts. So that is the list of abbreviations they are given. Second one, memory and bus architecture. So in the second uh, index, okay, in the second index, if you just see this one, they have been given the memory and bus architecture. So in that, you can able to understand system architecture, memory organization, memory map, and boot configuration. So in the system architecture, you are having the multiple buses. Yes, I'm just showing you this one. So six masters are there. Okay, and these are the five slaves of it. So this is going to be called all the buses, which is called as a here slave. So here we are just using whatever the buses which is going to be using for the like processor and memories. It is masters. Okay, so the buses which is used for normal SRAMs and all, it is going to be five slaves. Okay, so there is a two types of system architecture. We can able to understand. So this is okay, so I'm just opened this data sheet. Here you can able to see the page number 15, the complete block diagram. So in this processor, you can able to see the D bus, instruction I bus, and S bus. Okay, so here what is D bus and what is I bus and what is S bus? So everything they have been given in this memory bus architecture. First of all, in the system architecture, specifically discussing about the complete bus details. So that is the thing. Okay, in this reference manual, this bus architecture system, which is completely speaking about the complete bus. So what is the DMA bus memory bus? And what is internal flash memory I code bus, D code bus, IHB bus? What does mean? Okay, so in this scenario, we will see it everything line by line. First of all, in the system architecture bus, we are having these are the buses which are having, right? So first of all, I bus means it is instruction fetching bus. Okay, so it is this bus is specifically going to be fetching at instructions, and this bus is for specifically going to be data, both code and data, unlike its I bus. Okay, and third one is a system bus used for accessing the peripherals and ESRAM. Okay, so these are the things which is actually doing. For example, if you just see one example for, I'm just have to send the data. So instructions mean, so you have to send one instruction. So A plus B, this is the code you are going to be sent. Okay, and here you might be used A is equals to. Okay, so you have been already declared A is equals to 10 and B is equals to 15. So these are going to be considered as a data, and this is going to be considered as an instruction. So instructions are going to be sent through different bus, and these data are going to be sent through the different bus. And accessing a data in peripherals, we are going to be using a system bus. Okay, so if you are sending any data like this, okay, so from peripheral, you are going to be collecting a data, right? So in this data sheet, while you're going to be read this one, so if any data, for example, ADC, which is collecting a data, analog to digital converter, going to be happening. So it is collecting a data that is going to be sent to the processor, going to be processed. So this collection of data is going to be completely sent through this system peripheral. Okay, system bus. And a TMA bus, so it is having a direct memory access is there. It is going to transfer the data between the memories. TMA peripheral bus, so this one is can able to accessing through your buses. Memory to memory transfer only going to be happen, but here the bus is going to be involved. Okay, and the bus matrix means you can able to have the central component, that is a central access for the multiple bus. Okay, if you just see this Yes, here it is called as an AHB bus matrix because this AHB is going to be separate as this is AHB2, this is AHB1. So here also you can see one bus matrix. It is actually aggregating like AHB, ABP and AHB, ABP1 and all. So a lot of buses which is going to be splitted from here. It is going to be called as a bus matrix. Okay, it is going to be called as a bus matrix. So in this embedded system, okay, so these are the things which is actually present inside that. You can also check in this ARM Cortex processor, what are the buses which is going from them. So here, this is the processor. There is a three buses, D bus, I bus, S bus. From this Cortex M4, right? So that is what here it is going, three buses which is going, instruction data and the system bus. And from DMA, what are the buses are going? So from seeing it here, so you can able to understand. So what are the buses which is actually going from the DMA? Okay. So if they are not mentioning, so they are, you can also check it on here. And from Flash, what are the things which is going on? And these are the microcontrollers, peripherals. It is I code and D code coming from the Flash memory. Okay. So in this Flash memory, it just using this I code and D code. So and then peripherals. Okay, peripherals. What are the things which is actually using? So this is how the bus matrix which is working. So that's it. So next thing, if you just scroll down, here you can clearly understand the concepts. Okay, so here they just given the diagram for what buses which is actually having, and what is I bus? So I bus is connected in the instruction bus to the bus matrix. Okay, that's actually used to go to fetch the instruction. Data bus, it is going to be help you to the data bus of the Cortex M4. What is actually going to be doing? It is the literal load and debug access. So target of this bus memory code or data. So it is actually bringing a data and finally the system bus which is actually going to be fetching a data and all. Okay. So likewise you are having for each and every DMA bus and DMA peripherals and buses like AHP, ABP buses. So in our projects and all, so we had done first of all, before going to be work on with all the peripherals, we have to be enable this RCC register. Okay, so this is all the thing which you have been studying. But previously, guys, this RCC register. So while I'm going to be teach you that whatever the peripheral, like if you want to enable the GPIO, if you want to be enable the timer, so you have to be check for which bus it has been connected, and clock you have to be enabled through that. So the data has been given here. Okay. So why you have to be do this one? So you are having a two AHV ABB bridges. Okay, so one is ABP1 and another one is ABP2, which provides the full synchronous connection between the ABP and two ABP buses. So allows the flexible connection of the peripheral frequency. It is giving the flexible selection of frequency peripheral. Why we have to be used? Refer to the data sheet for more details of ABP1 and ABP2 maximum frequency. So if you want to be understand what is the frequency of ABP1 and ABP2, one is 100 megahertz, another one is a 15 megahertz. Okay. So this is fine. You can get this data. And address mapping of HB and ABP1 you are going to be know. So here your data has been given here. After each device reset. Okay, once you have been power off, it is reset. Once you are going to be power on also, it is reset. Okay, because your microcontroller get reset. Once you power on the microcontroller, everything going to be reset. So in these conditions, all the peripheral clock is disabled. Okay, so once you just your device is resetted, all the peripheral clock has been disabled, except for the SL and the flash memory interfaces. Okay, except these two memory, okay, complete your peripheral has been resetted. Sorry, your microcontroller completely resetted. Before using a peripheral, you have to be enable its clock in this RCC of AHB and ADD. So that is the reason we are enabling these registers. Okay. So before going to be work on the peripherals. For example, if I want to be interfaced with any peripheral, it is in this condition of reset. Okay, it is in this reset condition. Okay, I'm going to be show you this. So I hope you have remember this concept. So when I'm going to be interfaced with any peripheral for an ADC, first of all, I'm just checking out which bus it has been. First of all, you're going to be find it out the which peripheral you're actually going to be working on. Okay, and after it is connected with which bus you're going to be checked. And if you find it out GPO is connected with which bus. So with the help of this bus, you're going to be give the clock pulse going to be enabled. You're just enabling this. So that concept have been given here. After each device reset, all the peripheral clock has been disabled. So except these two memory. So for that only, before going to use any peripheral, like you are going to be using ADC, GPIOs, or whatever you are going to be use, you have to be enable its clock in this buses. With the help of these two peripheral buses, you are going to be this is actually in the register format. By enabling the register, you can able to start the complete functionality. Okay. And when 16 or 8-bit access is performed ABP register, the access transform to the 32-bit. The bridges duplicates as well. So you have to be remember this point is very, very important. So for that, we just enabling the concept. So good evening, all the people. So Thirumal, good evening. And all the people are posted. Good evening, guys. So the thing is, next one, so if you just scroll down, it's completely for memory organizations. Okay. So we have been completed up to this process and all. You can easily understand, guys. So I just given the some overview of what is the bus is actually doing. All the bus, the common thing is transfer your data. Okay. So don't confuse it with the concept. So just understand it by basic. First of all, you have to be why you have to be using the bus means transfer the data. Here if you are having one resistor, okay, so after that resistor you are going to be connecting any for example you are going to be connect any peripherals. For example, you are going to be connect any voltage regulator or anything else you are going to be connected. So if you want to be connect to these two components, definitely you required one wire to connect these two components. Then your your current will be passes through this wire. Okay, so same thing, you are having a two peripheral, for example, GPI and another peripheral. So you are having multiple. So everything has been connected through bus because here we calling the name of bus. So it is transferring the data through that bus. Okay, so that is the common of bus. But in this bus, we are having the different types of bus like D bus. So yes bus. So C bus. So I bus. Sorry. So and DMA bus. So why we are using the multiple buses and all? Because not it's not a current common current going to be sent to transmit to every peripheral. We cannot use the common wire. No. Here we are using a different type of thing. So we are going to be send the data in separate bus, instruction in separate bus, peripheral data in separate bus. If I send getting a DMA address data, it is going to be collect to the different bus. Okay, so that's what we are having the different bus. Don't need to confuse about this. Just to refer this page. And this is very important thing because we are going to be implemented in every project to be enabling this. That is the procedure has been given here. Okay, and then memory organization. So this memory organization concept, which you already discussed in this data sheet, right? So I already show this. This is present in the data sheet one. If you just go to this memory mapping, they have been given in this format. So for you can able to see the structure of memory. Okay, this is the SRAM starting and ending address. These are the peripheral starting and ending address. So this is the internal peripherals memories. So in this one, if you just see this one, so AHB2 and AVP1 and AVP2. So AVP1, these are the buses. The buses boundary address. So boundary address means starting from this to this. Meanwhile, we are having the unique address for each peripheral. Okay, so likewise, you are having the starting to ending address. Okay, so for here your peripheral is going to be placed, but here if you just see this one, flash memory starting to ending address is this one, and system memory ending to starting to ending to this one, and then you can able to extra memory. Okay, so here you have to be understand one concept. We are having the, I told you while I'm going to be teach this concept. Okay, so page number 15, they have been given the data of page number 1. In this data, we are studied like there is a two types of memory. One is a flash memory and another one is a SR memory. So more every microcontroller, okay, this concept is very important. Every microcontroller as having a two type of memory. One is a volatile memory, another one is a non-volatile memory. Okay, so this volatile and non-volatile going to be used for storing your data. No, volatile, non-volatile, not going to be easily erased. Flash, ROM kind of memories comes under this. When you upload this code, first of all, it's just going to be dumped into this flash memory. While at the time of debugging, or at the time of runtime, your data is going to be temporarily stored and processed. The processor is actually going to be used this volatile memory for to be at the time of processing easily to be fetching the data because it is comparatively fast. Okay, this is the common scenario. But other than that, you will have some very important memory that is called as a system memory. So in the system memory only you can get the bootloader. So the bootloader is going to be uploaded on the system memory. So when you're going to be power on your microcontroller, first of all, this bootloader is going to be on, and then only other things are going to be started. So here they have been mentioned like page number 15, 53. So I told you here. So there is a different memory. The mentioned memories are, one is the SRAM. Okay, so one is the SRAM memory, which is having 128 kilobytes, and another one is the flash memory. It is also mentioned. So you can also get the starting address to ending address of this. So these are the peripherals holding. So for that, it just having a different starting to this address. Meanwhile, so if you want to be find out what are the peripherals which is connected in this ABP one, you can simply see it on here. Okay, here they have been given what are the peripherals has been connected ABP one. So yeah, here the ABP one. What are the peripheral which is connected? PWM, I2C, 3, I2C1, I2C1. So all the peripherals having a certain boundary address has been given there. Okay, this is the thing it is. So you can able to get all the peripherals addresses you can able to get through this. Okay, so you can able to get the all the peripheral addresses. So okay, and in this case, guys, I'm having SRAM and flash memory just common for likewise how the memory has been presented and other microcontroller has been there. And other than that, you can able to see the system memory. So here only we can able to upload the bootloader code something. So it's just going to be help you to be boot whenever you're going to be power on your microcontroller. The small piece of code going to be run with the help of the system memory. Okay, so this is the complete architecture. We studied it already, right? So same thing has been they have been given in this one. It is memory mapping details. So memory organizations, how it has been organized, what is the size of those concepts, and same. So what is the boundary address of each and every peripherals? Okay, so you can able to get the boundary address, and you can able to get the what is SRAM. Okay, and the details of SRAM we can able to study it here. So it is going to be using I and D code. When boot from SRAM is selected from physical remap of this one, and you can able to get the data of the flash memory. Okay, so it is the main program memory block divided to the sections, and system memory from which device boot and system memory boot. So both which is required the system memory to be uploading your for to be initializing your code. Okay, and then so sorry guys, we'll start. So it's somewhat lagging. So here also you can able to see this one. So I'm having a bridge connected buses and all we have been completed. Memory organization, in this memory organization, yes, as I already show you that we will get the boundary address of every peripherals. You can study this. Okay, and the embedded flash and SRAM memory, you can get the overview. What is flash memory and what is the SRAM memory details and all you can get. So the normally flash memory, which is the non-volatile memory. Okay, so the data which have been given here, so I just tell you the few points about this overview. Okay, so it is a non-volatile memory. Store your program and code. It is constant. So it is actually divided into the sectors. So it is allowing the efficient arrays and write operations. So it is actually doing the ART, adaptive real-time accelerator for fast instruction fetching. So because your memory, your processor, this is another memory. How it is actually going to looks like. So this is your flash memory, and this is your processor. Okay, and this is your SRAM memory or volatile memory. Okay. So while you're going to be uploading your code, it is going to be stored on this flash memory. So the processor will fetch the every instructions. Processor will be fetch the instruction and then process at the processing time it's temporarily storing your data on the system memory. That is what this is how the flow will be looks like. But in this scenario, it is actually fetching the data. It is going to be called it as an AR, not for fetching the data. Fetching the data, the timing. Okay, like if I want to fetch the data without any delay, first of all, it just fetch the data. This is data one. After, without any zero point 0.1 millisecond delay, we want to fetch the another data. There is no delay going to be happen. It is going to be this ART. It is actually going to be called it as an so adaptive real time accelerated for fast fetching. Okay, it is actually being like zero wait seconds. Okay, zero wait time for fetching the data. So each and every data is going to be fetching very fast. So how much data is actually fetching? So thrice to millions of data for fetching. It helps to fetching very fast. Okay, here data sheet has been mentioned. Here, this one. So this Cortex EM4, it is a 2 byte band regions. So it is one of the formula, guys. The mapping formula shows how to reference to each word in this alias regions to corresponding bit band and bit region. So mapping formula. Okay. So what is this formula is actually telling you is so this is the formula. You just say it on here. I'm going to be show it also. Okay. So before that, we will complete this extra memory also. So I didn't get you, Tirma. So captions are not available. So do you want to turn off this captions? So the icon will be over. So you just use that icon or reconnect it, guys. So it is going to be okay. So here SRAM is actually going to be used at the runtime variables. It is going to be showing. It is going to be using the runtime variable and stack and heap. It is comparatively faster than flash memory. Okay, that's what the processor which is using this SRAM for this volatile memory for this at the time of processing. Okay, so directly accessible via the data and SRAM memory. It is the size of this one. So these are the things we can able to get it at the SRAM and flash memory. And another thing is the byte banding, bit banding and boot configurations. So what is mean by bit banding? Okay, what is mean by bit banding is normally your microcontroller like STM32, which is using a 30-bit register for controlling the peripheral. But if you want to change only one bit, you must be read the entire 32-bit register, modify the single bit. Write the entire 32-bit value back. So, for example, you know that this concept. So, how you are just configuring all the peripheral registers here? Yes, here, or each, if you're just taking each and every peripheral which is holding a 32. So 32-bit registers, we just calling as and each, because the processor, it is a 32-bit processor. Okay, so in this time, if you read the entire 32-bit and modify the single bit. So, yeah. So, for example, here I've been given the example for this. Okay. So, yes, you can easily understand. Yes, for example, I'm just using a ODR register. Okay. What is ODR? It is the output data register. We have to do an hands-on. So based on that, you can understand. So GPIO inside this, you are having ODR register. So in this, with the help of this ODR register, output data register, if you want to controlling the output peripheral, for example, LED, you are having motor, you are having. With the help of this ODR register, you can able to control the on and okay. If you want to read any data, you are going to be using IDR register. So having a different register going to be very based on application. In this case, what you are going to be doing? We have to be write the address first. If you want to be modify the bit file, for example, you are using a GPIO or fifth pin you are using, then you have to be turn on the fifth pin on and off going to be doing. So for that, you have to be use the entire 32-bit register. So in that, you just modify the bit. So if you just directly only want, so this is how you are going to be. So this is the normal method. So GPIOA. So in this GPIOA of ODR register, modify the fifth bit as well. Set the bit as well. So if we are using a bit banding technique, this is the formula. Okay, you can specifically manipulate that one bit. Okay, so the formula they have been given. Yes, you can use the bitwise Varnasutta, but here they have been given another technique. Another method, we call it as the bit banding. Oh, sorry, bit banding. Yeah. So in this bit banding, you can able to address or band or number. So anything you can able to manipulate. The formula, so bit band base address and offset byte offset value into 32 plus bit number cross form. Okay. Here you can able to see this one. So this is the formula for your when. First of all, you have to be write the bit band base address plus byte offset value. Okay. So this bit band base and byte offset value is the address of value. So you can get it from the data sheet and register. So this is the address of this ODR and this is the byte offset value. Okay. Into of 32. Okay, into of 32 plus bit number you want to be manipulate. I want to be manipulate the fifth bit because the GPIO fifth bit, GPIO A or fifth bit I'm going to be connected, right? So in this GPIO fifth bit I want to be connected. I just use that bit number into of 4. Here I've been using here they have been using a fourth four you have to multiply the this is the actual formula. Okay, so you have to be using so while you're going to be using this value, you can specifically manipulate the setting that. Okay, you can easily going to be set the bit as 1. So based on the value which you're going to be getting, so you can easily manipulate the complete scenario. So this is what the bit banding technique. And next one, it is a boot configuration. Okay, the boot configuration. So here also they have been given. So the address into the offset value of 32, the pin which you want to be manipulated, and okay. So this is your peripheral address. Okay, the peripheral address means which bus you are just connected. For example, ABB or in that you want to be specifically manipulate the which G. So inside that you are going to be mention the address of that ODR or somewhat. Okay. So in this ODR address plus this is a base offset address. So you can able to see and check it here. So here I'm just first of all check the address value. So first of all, which bus it has been connected, and then you just manipulate it, and then you just find it out the ODR address. So this is the address you are going to be used, and the base address, byte address you are going to be used, and the 32 multiply with 32, and which bit you are going to be actually going to be manipulated. If you want to be manipulate fifth bit, you just use the 5 cross 4. So you just implemented in this address, you can easily get the bank. Okay. So that is the thing. And boot configurations means. So the boot. So what is meant by boot? It's explanation of each boot. We are having the memory boots of different boot modes. First of all, the flash boot. Okay. Flash boot means the normal execution mode for your program. Okay. So run user program for flash memory. So you're going to be this bit is actually going to be in 0 page. So if you want to use the firmware updates, okay. So that time you're going to use the system bootloader mode. If you want to be firmware going to be update like this is 0 and this is when boot 0 is 1 and the boot punt is equals to 0, which is entering system to the bootloader. Okay. And firmware update means you're just trying to upload your code into your microcontroller. For used for debugging bootloader, so you are going to be enabled this. So everything, the boot configuration has been given over there. Okay, so this is the thing. So you can also given the embedded bootloader. So embedded bootloader mode is helps to reprogram the flash memory. So which is with the help of if you want to be reprogrammed for each and every peripheral, you can able to use this pins. Okay, for UART one, UART two, I2C1, I2C2. So it is going to be help you to reprogramming your flash memory as well as how much clock it is actually required, 16 megahertz clock. And you have to be using the HSI or HSC is going to be possible here. Okay, so that is what they have been given, and it is the bootloader mapping value. Okay, we are going to use any of the bootloader mapping value. This is the address you are going to use. So till now we didn't work on this bootloader yet. So we are going to be study this. We are going to be work on this bootloaders concepts and in upcoming sessions. Okay. And then we have to be study about the embedded flash memory interfaces. So what is embedded flash memory interfaces? So if you want to be flash memory interfaces in HTML32, it handles the program and erase the operations. So we know SRAM memory, once it is powered off, it is automatically the data going to be erased off. But in this flash memory, we are going to be handle with the power. Okay, so program going to be not easily going to be erased off. So for that one, what are the key features of this one? Support the single and double words programming. So you can able to do this single and double words. Erase operation include the sector erase and mask erase. So you can also see this one if you want to be erase the codes. So this is the complete flash memory interfaces. Okay, so you can able to get what are the buses has been connected on this flash I code and D. So you can easily find it out. This is I code and D code. Pass has been connected on this flash memory. Okay, so it is inside the registers is also there. So because of to be if you want to be write the code, so rewrite the code, so you can able to possible. And the bus which is connected is AHP32 bus. Okay, so they have been mentioned. And the features we can able to flash memory read operation. Mostly we can able to once the code has been uploaded, so you can read the operation. The program and erase can able to pause happen. Read and write operation can able to happen. Refetch the I code and 64 catch lines of 128 bits is possible. It is 8 catch lines which is possible. So this is the flash memory. But okay, access the instruction in flash. Okay, so as well as access data and literal pool in flash memory. Okay, so these are the stuff which is actually going to be possible on this working environment. So flash, we just interfacing this one. Okay, so the data, guys, it is mentioned as in data. Okay, so this is the architecture of flash memory. So flash memory interface with connection inside the system architecture. So we have to be see this how it has connected with the system architecture. So this is bus, it is a system bus. So it is also connected with this flash. So because of you are having this one, so you can also rewrite the codes and all. It is possible. So if you want to be access the flash with it is register access going to be with the help of this FL ITF. Okay, with the help of this register, I can able to do this one. Okay, so it is a flash interface, and this is the exact flash memory. Okay, so it is a flash interface, and it is exact flash memory we are going to do, and then programming the flash memory. So how you can able to programming the flash memory concept and all. So must be unlocked before going to be write. So you have to be unlocked it before going to be write. Writing to flash memory requires a write sequence involving a setting specific control register. The flash status register is also there. So flash is also having contained the specific registers. Okay, so flash is also containing the specific register. So you can able to see this. So with help of this, we can able to write the code, rewrite the codes can also possible here. Okay, you have to be read it every flash interfaces. So flash access control register. So yeah, it is having ACR. So you can able to control the register. So data cache reset, instruction cache, data cache enable, instruction cache enable. So everything. So the latency. So if you want a key register, so it is going to be used for the different purpose. Program and erase operation. If you want to be program or erase, so based on this is possible. So key register. So it is going to be used for the different applications. Status register. You are going to be checked whether it is any ongoing, it is programming or erasing the operations. If you are having the memory, flash memory, whether it is putting or whether it is programming your flash memory or just erasing the data. So with the help of the status register, you can understand it. Okay, likewise, you're having the control register, starting the flash memory, like to be configure or going to be program or going to be erased. So controllability going to be happen with the help of this register. Okay. So that is also possible. So we are having the different registers about this flash memory going to be protect your stuff and configure and reconfigure. There is operation, so that's also we have been studied. So it is there's two types of arrays. Once you can clear the data and sector. You can also do the mass clear arrays. That means you can completely clear the flash memory which is present inside this data. That is also possible. So all because you can use it in this register. So if you want to be specifically interface any flash memory, you have to use this registers. Okay, you will get the complete register mapping. So what are the register it is actually having and each registers. So what is the position? So instead of you just go to every register step by step, you can easily check it on here. This is the offset value. Okay, so you have to be having some boundary value plus you have to be add this offset value. You will get the exact register. Okay, in this all are reserved. These are the register which is present in this ACR register. This is latency. You will just see this key. These are the registers just having OP KT key. These are registered just having as a status register. These are the busy program registers and all just have control register. These are the register. So likewise, these are the offset value you are going to be add with the your boundary address. So then you can easily find it out with the this memory structure which is present in every registers. Okay, every peripherals. It is having this option. Okay, so this is what the boot, sorry, flash memory. Okay, and then you can able to see the CRC, so flash production is also there. So what is CRC? It is cyclic redundancy check. So it is used for the data integrity verification. It helps to detect changes in stored data due to transmission errors. So if this cyclic redundancy check, we are going to be do with the multiple kind of. So the cyclic redundancy check going to be checked by the using of this polymorphisms, a polynomial technique. So this is a polynomial technique as going to be used. Okay. So if you are having get the data, it is going to do with help of this polynomial technique. So you might be studied in mathematical application. So it is going to be implemented that and a single input output 32-bit register is going to be checked and going to be verified whether it is having a good correct CRC. So that parity and parity check is also going to be happen. So whether your data is this correct format. Okay. So this CRC check it is going to be calculated when writing into the register. So hold the result of the previous CRC reading when reading the register. So while you're going to be reading the register, you can able to give. Okay. That is the CRC. If you want to be specifically see the CRC register, it is also some registers in this part. Okay. So just having a data register, independent data register and control register. Okay. The complete mapping. This is the complete register which is present. Data, IDR and control register. Okay. Because we cannot change it. The incoming data you can able to verify. You're going to be verified. Just collect those data register and going to be verified. Okay. And if it is anything is not going to just completely reset your code because the data is going to be giving some errors or any issues going to be happens. Okay. So and then we have to be check it for the power controller PWR. So what is the purpose of PWR is? So this is we are already discussed this concept in this data sheet. So how your microcontroller is going to be work in this different mode. So power consumption concept we studied this. So if your microcontroller is completely running all the peripheral, that is your processor is completely working, how much current is using and what is the frequency, 100 megahertz of 100 microamps it is. Okay, so that is how we are having the power control system. So if your complete microcontroller is turned off, it's just using VBAT. VBAT, it is running in backward because this RTC is never going to be turned on. It is a real time, right? So it is never going to be turned off. It is completely this VBAT is running for to be giving a backup circuitry for your RTC. Okay, so the backup registers are also going to be turned. So for it is your CPU is currently working. So how much current is actually going to be taking, and what is a frequency range and all. So they have been given. So normally we are going to be segregated normal mode. Run mode means it is normal operation. Sleep mode means your CPU is stopped and peripherals remains active state. It is not completely turned off. So stop mode means it is using a low power consumption, so the RAM content time. So standby mode means it is completely reset. So microcontrollers reset. So likewise, we are having the different types of operations. We can able to check it out. So up to here, if you got clear, guys, you just post the message on clear on the chat. So I'm going to see how many people are clear. You just post the message clear. Nice. Yes, Mukesh Thirumal and all the people have been posted in the pod. Varnit Gupta got clear message posted on the chat box. So happy to see you. So super guys, and we'll continue this session. Okay. And so up to now, we just discuss about the current, how much it is actually going to be taking. So, and everything we have been discussed. Okay. So you can also see the ADC converter, supply and reference voltage. So this is we have been studied in ADC. Okay. So what is a because it's actually going to be reading the value as a voltage. So this is previously we discussed in this ADC concept. You just refer that video, guys. Okay. Now we can understand this concept. Okay, what is the reference voltage of ADC? Okay. and input voltage of ADC, and what is RTC is actually going to be taking a power. And yes, so all those stuff has been given here. And configuring a ADC. So if you want to be configuring a ADC, so these are the register you're going to be actually going to be use. Okay. So the complete thing is this one. So this brownout resets and all we discussed in this concept, and a programmable voltage detector. So whenever your microcontroller go down or below the operating voltage, it is automatically reset. If it is above the range, it is going to be reset the value. Okay, because it is going to be causing some issues. So that is what it is actually going to be using. Okay, and then so this is about the complete flash memory, CRC, and all. So next we will discuss about this RCC, reset and color control register. Okay, so here after only we can able to see this the complete registers. So this registers means what are the register in microcontrollers? Okay, so the registers are small storage. First, most of the time we are using a okay, okay. Am I audible, guys? Guys, am I audible? So am I audible? You just post a message called as not. Okay. Okay, so in this one, guys, sorry for this interrupt. It was some hang which has happened in my laptop. I accidentally touched the close button. Okay, so I hope it is audible now. So what we have, where we have been left. Yes, this is the concept which we have been left. So the registers are small storage locations inside this microcontroller. So most of the time, I'm using the word called as a register, register. All the peripheral which is having a register. What is register? I told you already, the memory is different, the register is different. Memory which can able to store the bulk amount of data can able to store, but register is not. So only the bits of data only going to be stored by this register. Okay. So if you might be heard about it is a 32-bit register. Okay. So if you are taking one register, ODRS register, it should having a 32 bits, like it is having the multiple bits like this, or inside this you will have some bits. So if you want to be toggle any bits, you can able to specifically can toggling the any of the bits. Okay, so you can also see it in this reference. Okay, so it is having a 32 bit. For if you're taking any registers in it, for example, I just randomly taking the CR register. So CR register is one of the register. You just consider, you just imagine you are having a rectangular register in your hand, which is very minute. Inside that, you're just having the bits. Okay. So every bit just holding a different types of bits like HSI, HSE. So high speed external clock. Okay, likewise, they are having. If you are going to be enabling one bit, so we cannot manually do it by programming itself. We just done this concept. So by doing this, we can able to what can we say? So it can able to on and it can able to be done this specific. So for all the register, that's what it is, a 32-bit register process. Okay. So if it is taking if you are using this register, it is consider the whole register. If you are working with only the 16-bit, if you are telling like I'm just working with the 16-bit only, it is considering the complete register. In that register, you want to be enabled the 16th one. So based on that, it is actually going to be okay. You got it clear. So I just tell you this example. Okay. So this is the register. What is register? We can clearly study it. It is a small storage location inside your microcontroller or processor. So inside your microcontroller processor, it is one of the storage. That means storing a data. So they hold the data configuration setting, control signals, and required for the processor. So if I want to be doing analog to digital conversion, okay. If I want to, for example, just to show you, I want to do this analog to digital conversion. So for that, what are the register which is mandatory required? I'm going to be taken that register, which is present in your ADC. Okay, this is the ADC which is present in your microcontroller, complete microcontroller chip. So this is the ADC. Inside this ADC, you are having a CR is one of the register, which is a 32-bit register, and ESR is one of the register, which is 32-bit register, and likewise DR is one of the register, which is 32-bit register. So in this 32 bit, if you're using only one add-on bit, it is taking the CR register. So the processor will taking this complete CR register, completely taking the 32 bit and process. That is what is a 32-bit processor. Okay. So the completely taking a 32 bit and only process this add-on bit going to be turned on. So while it is going to be on, this complete ADC module is get. Yes, guys, I'm going to be sent the link. Okay. So don't worry, I'm going to be sent this link. Okay. So in this case, you can able to see this when you are having the multiple registers, which is going to be on and off and processing the data. It's actually going to be using here. Okay, so in this case, next one, the register plays a crucial role in interfacing with hardware peripherals, memory, and CPU processing. So whatever you want to be do, so it is actually doing the processing of the 62-bit register. Okay, just to get processed. Okay, I hope you got clear this point. And so now we have to be discuss about the special function register. So what is the difference between the register and special function register? So the register, which is commonly available, commonly, if you are taking any microcontroller, you might be heard about the general purpose register, which is commonly storing some bits of data. Other than that, the special function registers are now we speaking about like inside this ADC. Yes, Gopal, I'm going to be send you the link. I asked my team to send this link. Okay. So in this one, in this ADC, you can able to see the CR. Yes, sir. These are the specially registered. Why we call it so specially registers are. It is only designed to for this ADC. The addresses are going to be assigned. So address, the specific address for CR register. So SR register. So if while using this ADC, control register of ADC, only you can able to manipulate the ADC. So likewise, it was assigned. Okay. So for that, you have to be understand this concept by this one. Okay. So there is a two types of register, normal register, and another one is a special function register. So we are using a special function register for your peripherals. Okay. Yes. Super. Okay. I hope you got clear. So we will go to this next one. for the special functional registers. So after it is completely having only the special functional register, we are going to be studying. Okay. So I already told you why we are using this RCC register. So they have been clearly given in the concept. Okay, they have been clearly given in the concept. This is you have to be refer. So all the peripheral, whatever the peripheral you are going to be working on. Okay, so likewise here this is your peripherals like GPIO and timer and all. So in the beginning you have to be enabling the peripheral with the help of this buses AHB or ABP or so through this RCC register. So in this RCC register, by using this buses, you can able to enabling the you can able to all the peripheral or clock previously is disabled after each is going to be reset condition. So before using the peripheral, you have to be enabling the clock with the help of this methodology. So that's what we are just actually doing this work. So this RCC register which is completely used for enabling your peripherals. So you have to be check with the peripherals. If you are taking a user, check it is connected with which bus. Before that, you are going to be check the GPI open. So after finding out the GPI open, you have to be check the GPI open is connected with which bus, and you have to be make sure enabling the okay. Make sure you have to be enabling the buses. Okay, it is very important concept. So then only you can able to proceed that stuff. Okay, and then we have to be go to the reference manual. Okay, you have to be go to the reference. So in this reference manual, they have been given the special function registers. Okay, so they have been given the special function register. So we will see each and everything by step. So why you're using that and what the procedure we are going to be made it. Okay. So because each are very big process, guys. So while doing a project only you can understand. I'm just telling you how to see the procedures. Okay. And configurations. Okay. For example, if you're doing one project, first procedure, what you're going to be do? First of all, checking the peripheral and enabling the peripheral with the help of this bus. So you're going to be checking the RCC register. Right. So in this RCC register, based on this HB1 or so based on using this RCC of AHB1, you have to be enabling the peripheral. This is the very first procedure you have to be doing after come after this reset condition. And after this, when RCC register have been completed, you can able to see the system configuration general purpose register. So these are the unique ones. So if you are going to be work on this RTC, you have to be use this RTC register. If you are going to be work on this ADC, you are going to be using a ADC register. Okay. So these is the very common stuff you are going to be okay, so based on that, which register you are actually going to be using. So based on that, you have to be configuring your registers. Okay, for example, this is system configuration. So line panel will come. First of all, RCC register. So why should we use this clock in the system configuration? Microcontroller, the clock signal is very essential to drive to the entire system. Without this clock, the microcontroller instruction is not going to be sent properly. So it is in the reset condition. For that, we are having the different registers. So if you want the phase lock loop, we can also implement it. Someone asked in this slide, so how to maximize the clock? So you can able to, with the help of this phase lock loop, you can able to maximums and dividing the clock. So multiply and divide. Just having only the 16 megahertz, but your desired value is 100 megahertz. By using this division and multiplication, it is actually going to be possible. Okay, you can able to implement this uh, circuit by here. Okay, so yes, that is possible because it is having an inbuilt here. So if you want to enabling the peripherals and all for LED and anything want to do, you have to be give the first of all you have to enabling the peripheral with the help of this bus. So that is the first procedure we have been doing. And then they have been given the system configuration. So Second thing, they have been given the system configuration. The purpose of the system configuration is external interrupt when you want to be do that, and GPIO signals, and inside this peripheral inside. So mainly the system configuration is used for, if you just read out this complete thing, this is just external peripheral interrupt. If you want to be, if you are configuring the interrupt, that is the external one, you have to be use the system configuration. External interrupts are not going to be used. And then you have to be seeing this GPIO. Okay, you can able to see this GPIO. What GPIO going to do? Okay, so the concept is your all peripherals has been definitely connected with this GPIO, because I can't directly work on this SPI. You have to be definitely interfaced with GPIO. Okay, it has been definitely connected with any of the GPIO. SPI having a different pin like MOSI, MISO, chip select, clock pin, kind of multiple pins I'm just having. So all the pin has been connected with any of the GPIO pin. So with configuring that GPIO pin in your program, you can able to work, you can able to transferring and receiving the data. So GPIO is a common thing for all the application, all the process which you are going to be doing. Okay, you have to be definitely find it out, which is presented in this pin definition. Okay, if you want to be checked for this, each pin has been connected with which one, we can able to get it easily. So what is it? It's SPI4 if you're using. SPI4, if you want to be checked, the MOSI pin is connected with which pin? It is a GPIO of the pin. So if you're using SPI4 of MOSI, so it is connected with PE of yes. So likewise, chip select pin where it actually connected. So you have to be find it if you want to be find it for the each and every pin. So it is going to be possible here. Okay, pin definition. That is good. So that is the very important thing of GPIO pin. So here they have been given GPIO H and 0 and 1 is not available. So while you're going to be open up the each peripheral details, initially they have been given the detail. Like what are the peripherals? What are the GPIO peripherals are available? What are the peripherals are not available? Okay, so they have been given. Okay, so yes, guys. So super excited. So super Thurman. So super for your happy for your answer. So thank you. So up to 8, how many people have got clear this message, guys? If you got clear, just post clear on the chat. So you got clear. Tirmal got clear. GG. Superb, Tirmal. And we will move to this one. So in this GPIO guys, general purpose register, we are having the multiple general purpose register like mode R, like O speed DR and O type, and like we are having the different types of registers. So how can I understand about this register? First of all, you just study about what is GPIO. Okay, general purpose input and output alternative analog configurations. Just study it. Other than that, you can also do the electrical configurations. So up to each, which is having 16 input and output, control can able to happen. Output states, it is push pull or open right or pull up or pull down is possible. If you are using a output state, okay, it is in the different variation is possible. Okay, we already discussed about the GPIO pins detailing in this previous days. There is a different types of configuration: input, output, alternative, analog. So in this configuration, if you are using output state, it is having a push pull, open right, pull up and pull down. Output data we have to be taken through this output data registers. Okay, so if you are using a peripherals, it is using alternative function output. If you want to be control the speed for each input, speed selection is also going to be possible. For that, you have to be study which is going to be suit for this. Okay, so I'm going to be telling you that. Okay, so I don't want to overwrite it. Okay, so in this one, first of all, you just having this output state. If you want it to be select the state of the output, whether it is a push pull or pull open right. So you have to be use this output state. Okay. It is having a different register. If you want to be output data register from output data, you want to be fine. Output data you are going to be sent with the help of this ODR is possible. If you're using a peripherals, you have to be using the alternative function output. Okay, so you can got an idea about this output data register whenever you're configuring a output mode. Okay, so if you're using an alternative function, you're going to be whenever you're using a peripheral speed selection for each input and output mode. So it is also possible. So if you're using an input state, if you're using input, these are the things are possible. One, it is a floating. Okay, you have to make it as an open train. You have to be make it as a pull up or pull down. Okay, so other than that, it is a pull up or pull down. You can configure as an open state, or else you can use it as an analog, because analog means you can read it. Okay, read the data as well as pull up or pull down. So if it is defaultly pull up, so if you just it is defaultly in high condition or low condition, you can able to read the data. So these are the things that is applicable for the input state. If you want to be work on this input data, you have to use the IDR register. Okay, so input data, if you want to be collected, you can use this input data register. Okay, so it is actually going to be possible on it. So what the register you want to be actually work. Okay, so input data and output data. So bit set and bit reset register. Bitwise writing access. For example, you are using the ODR register. You can configure in this bit set register, bit set and reset register. Yes, guys. So sometimes your GPIO pin has this condition. That time you can able to use it as a you can use this pull up and pull down configuration as an input state also. Okay. And locking mechanism. So that time it is actually when it freezes, it is used for this register. Okay. And then analog function. So you are having an analog function also can able to possible. So after that alternative function, input or output selection register, we're just using a 16 AF. Okay. It's just up to 16 alternative function input and output mode. And a fast toggle is also possible. 2 clock cycle is going to be. So we are having the required registers has been given over there. Okay. So functional description. So specific order characteristics listed in the data sheet. So they have been listed in the data sheet of the general purpose register. Several modes are input floating, pull up, pull down, analog, open train, pull, push pull, alternative function, open train, pull up is going to be varies. Okay, so each bit is freely programmed to have a 32-bit words. So it is having 32-bit words. So it can also possible half words and bytes also. So purpose of BSRR, it is going to be used for atomic read and modified access of the GPIO. Okay, so this is how it is actually going to be looks like. So yeah, registers inside this GPIO, it is actually having the alternative output modes. Everything has been configured in this one. Okay, you can able to check the modes at all. Okay, so after this, you can also see this GPIO general purpose registers. So how it is actually capturing the data and why we are going to be using output data register. So in different configurations they have been given. Okay, so peripherals alternative functions of map AF1 to AF13. So it is used for the different applications. So for the previously we had did one procedure they have been given here. So each input and output mode has multiplexer with 16 alternative functions. Okay. So in UART and I2C, SPI, a timer, while we are going to be work on this peripherals, we have to be using the alternative function. Okay, the GPIO pin. In this GPIO pin function, we have to be using this AFRM. Okay, because the microcontroller input or output pin is connected to the onboard peripherals through multiplexer that allows only one peripheral alternative function connected to the input or output at the time. In this way, there is no conflict between the peripherals sharing the same input output. So while it is going to be sharing the same input and output one. For example, you are using a multiple port of 6 to 7, so multiple pins you are going to be using. This time you should definitely going to be get mapped. Okay, so it is input and output pin multiplexed. So your GPIO pin, so input and output pin is actually get multiple function of pin is going to be do. So each input and output pin has a multiplexer with 16 alternative function. So for that, you just use this AF0 to AF15. That is actually going to be used, the AFRL you're going to be used. If it is 0 to, yeah, I mentioned, so 0 to 7, so you're going to be use it as an AFRL. If you're using an AFRH, it is 8 to 50. This function we already implemented in your program, right? So that is the thing. So in addition, input and output multiplexing. So whenever it is actually doing a multiplexing operation, you have to be do this operation called as an alternative function mapping. Okay. So likewise, if you are using a system called JTAG and serial quality debugger, so after each device is resetted, you are going to be assigned to do the specific dedicated pins immediately. Debugger host is going to be possible. Okay. So mainly we are using that. Okay, and here they have been given the configure the desired input and output mode in the GPIO mode are registered. Okay, so the peripheral alternative functions for ADC the desired input and output mode as analog. So you have to be configured through this MODA register. Okay, so configuring this alternative function in ODR in MODA register. So they have been given. If you want to be configure the alternative function, this is possible by the MODA register. So I hope you remember this. I don't want to be done with more concept. So in every project while we have been implemented, if you have missed out this, please go and watch that video. I hope we should take on this class first. You can easily understand the flow. Okay, so first of all, they have been given to enabling the access register for to be configuring to enabling all the buses to enable. So in this one, they have been given some data. If you want to use the output data register, the peripheral which is working in this output mode, you have to be using ODI. The peripheral which is working in the input data register, you just use this idea. If the peripheral which is doing multiplexer, alternate multiple function is just doing, you're just using the AFR or AFRH. Okay, so the configuring the design input and output in the mode register. Okay, so if you are configuring the input or output, which is possible in the mode register, as well as if you are configuring the ADC, that is also configuring with the help of the mode register. If you are configuring the alternative function, that is also possible in the mode register. For example, I'm just duplicate this page 146. Okay, here you can able to understand for all the peripherals is just having the mode like input mode, output mode, alternative function, analog. So all has been enabled through this mode are, so they have this data has been given here. Okay, so whatever the function you can do input output, you can enable the mode. If you are doing ADC, enable the mode. If you are doing alternative, first of all, you just enable the mode. After that, based on the application, if you are doing a input mode, okay, if you are doing a input function, okay, output function, if you are configuring it as output, you're just using output data register. If you are configuring the input, you just use the input data register. If you are doing a multiple function, you're just doing AFR. If you are doing analog, you're just using a based on this analog. Okay, so based on that only, we just configuring each and everything. Okay, so this is how it is actually having. So these are the alternative function mapping. This is how it is actually having. So this is a AFRL, this is AFRH. So 0 to 7, this is up to 15 pins. If your pin which is having 0 to 7, it just uses AFRL. If your pin is using AF is 8 to 15, you just use this AFRH. Okay, all the details has been given. So finally, input and output control registers are modar, OT type, O typer, and OSPDR. And this is a full power holder configuration. Modar register, O typer, OSPDR. So these are the complete registers you are going to be using. Okay. So input data register. So you can also read it from this one. Okay. So all has been given in this data, guys. Okay. So input configuration, how we can able to make it. Okay. So that's it. Alternative functions, how you can able to do. So analog function. So what function you need to do. So all has been having the different data. So while reading that concept, so based on that, here also they have been given whether you're going to be enable or disable. If you want to be configuring input, you just use this bit like 0, 0. So at the which position. If you want to be configure as an output, you just use 0, 1 at the position of which position you want to be enabling the bit. Okay, setting the bit. So based on that, you just enabling and made the disabling the concept. Okay. And then you can have this O type of. So it is having the different functions. So here also have been mentioned. The moda register, it just set the GPIO pin functionality. If you're using O type of function, the configuring the output type, whether it is a push pull or open drive. Okay. You have to be configuring that. So if you are using a O speed up, okay, so basically you require this open train or pull up configuration. So based on if you're using a I2C and all, you have to be configuring the thing. And in it's at the speed also. So what the speed it is going to be maintained. So in I2C, we have to maintain the speed. Okay, so medium or low speed or fast speed. So each which is having a different number you can find. And then it is a pull up or pull down configuration you have to be mentioned. This is the input data register. If you want to be read the data from GPU. This is output data register if you want to give the data to the GPU. This is the alternative function, multiple function access can able to pause it. Okay, and then it's for the interrupt. Okay, so in this interrupt, so whenever you want to do interrupt, okay, whenever you want to do the interrupt, you can configure this register, interrupts and events. So in this, when if you want to be configure the NBIC, so you can be able to get the data, tabular columns. So what is the address of this register? Okay, interrupt register address you can able to get it, as well as what are the register which you can use to configure this interrupt. Okay, everything you have to be study. How I studied for GPIO, that's how you can able to study, because in while you're going to be study that data, you can understand about the microcontroller inside the GPIO as having these register. If you're using the ODR, when I'm going to be read that data in the reference manual, I can understand, use the ODR for output pen. Alternative function for multiplexer work. Okay, so you can read that data. For that, if you're going to be use the interrupt, you have to be read the complete data. How many maskable interrupt channels is there, and how many priority numbers levels are there. So you have to be read all those stuff. So external event you want to be made. So these are the numbers for each and everything. Okay, so this is the external interrupt features, and how it is actually making the stuff. Block diagram is very important. It is actually telling the registers. So AMBA. Okay, so ABP bus, it has been connected. This is a peripheral interface. And these are the register just holding this interrupt, pending request, interrupt mask request. So you have to be understand the each register configuration and which one is actually going to be suited for this. So the hardware interrupt you want to be do. So this is the procedure you have to be maintained. Okay, what is the procedure for software interrupt? Okay, and extra interrupt you are going to be make it. So these are the data they have been given as a procedure. Whether you are going to be do the software interrupt, you just do this procedure. Whether you are going to be do the hardware event, you have to do this procedure. This is hardware interrupt section. You have to be do this procedure. Okay, so based on that, you have to be read out all the registers and procedure and implement your projects. Okay, and this is for interrupt. And then for ADC. Okay, so we already worked for this ADC. So ADC when I'm going to be open up the ADC, they have been clearly given there is no ADC 2 and 3 is there. Only it is having a ADC 1. Okay, so only we are providing you the ADC 1. And in this ADC 1 instruction, so you can understand what is the bit. It is a 12-bit resolution. You can have the 16 external sources possible. And the VBAT channel is there. So you can able to, the result of the ADC is actually going to be stored left or right along 16-bit data register. So you can understand the concepts of introduction part and the main features. So what is operating voltage, supply voltage, reference voltage? So what is the data? What is mean by end of conversion? You have to be understood the main concepts of this. Okay, so this is the block diagram, the internal functional description they have been. So what are the register which is present inside this ADC? They have been given. Okay, so this is how it is actually there. So injected regular channel, this regular channel, injected channel. Okay, so these are the registers are presented. Okay, and you have to be you see this, what's the operating voltage? So it is the reference voltage. It is the input and the operating voltage which can able to get. Okay, so in this one you can start to read it from the scratch. In this introduction part you can able to get the introduction of this one. Okay, so this is the ADC. If you're just taking ADC, what is a bit of ADC? What is the channels? And in this feature part, what are the things which is available? And voltage, operating voltage, reference voltage. And based on the timer, if you're taking, what is a bit of timer? And so all the data has been given. So after you will get the block diagram. Here you will get some data. So what are the things? You can visually see the internal structure. Okay. And after this, here start to read it from the scratch. Okay, so ADC on and off control. So what are the registers you are going to be used? So if you want to be read it every line, right? Definitely it is going to be used. Okay, so if you want to be ADC is going to be powered on, you have to be enabled the add-on bit. Okay, it is present in the CR2 register. So you just go to your, I'm just duplicate this file. You just suddenly go to the CR1 register. Okay, you just go to, in this register section is in different index. You just suddenly go to the CR1 register. In the CR1 register, you just check. Okay, we studied it as CR, right? CR2. In the CR2 register, you can able to see there is an add-on bit. While you're going to be enabling this bit, it is telling like you can, when add-on bit is set at the first time, ADC is going to be powered on. So this is the first work I have been done. Okay. So likewise, you have to be do. Second thing, what you are going to be do. So you are not implemented the code as it is. You have to be read it very carefully. Then they have been given the conversion starts when either SW start or JW start. So these are them. Then you have to be understand what is meant by SW, what is meant by JW. Okay, so one is a single, there is a different thing is there, it says W and JW. You have to be read it carefully. Okay, so if you are not understand that, you just go to the, find it out the registers. So they have been mentioned what it is actually going to be. Okay, so you can stop the conversion and put the ADC in the power down mode by clearing the add-on. If you want to be stop it, you just turn off the add-on bit. Okay, these are the data. And then they are speaking about the clock. Okay, whether you're going to be give the analog circuit or digital. So I've been given the clock to this ABB to E. Okay, so just like that, I'm just leaving. So after that, selecting the channel. Okay. So here you have to be channel going to be selected. It is a regular group or injected. So now you can study what is meant by regular, what is meant by regular injected, because two things are there. So study, it is a 16 conversion, it is a 4 conversion. The regular channels and their order conversion must be selected in this one. The total conversion is the regular group. Okay. So based on that, you have to be use this register. If you want to be do the 4 conversions only, you have to be go to the injected group. Okay, so based on section, you have to be selected and then single conversion mode. And here they have been given the continuous conversion. Okay, so you have to be choose it whether you are going to be single or continuous. So that's what they have been mentioned. We are going to use the continuous conversion. So because I need to collecting the continuous amount of data. Okay. So ADC going to be start new conversion after finish its new one. That is the continuous conversion. This single conversion mode, it is also doing the same process. It might be looks like same. So you have to register, you have to be in. So I want the continuous conversion. I'm going to be looking for this one. And you have to be enable the con pivot to one by external trigger setting the SWT. So here also they are speaking about SWRT of CRT. Now I want to understand it is the continuous conversion mode. It is a single conversion mode. Okay. So here also they have been given a regular channel. Okay, after you have to be enable this one. So the last conversion data going to be stored on the data register. So meanwhile, whenever you are looking for the register, check along with the data. Okay. If I'm just saying for the CQ or one channel selection, this is how it is there. So how you can return a code for this, you have to be identified. So that's what I'm just telling you. You can easily write a code if you are very strong in the concepts. Like if you are very clear in your what is ADC, if you are very clear in your intra, if you are very clear in your other peripherals, plus programming, you can easily understand. You can easily read this concept and understand the concept, and you can easily write a code for this. Okay. So here we just seeing for this one and the timing diagram. Okay. Whenever the clock has been started, this add-on bit is going to be enabled. Okay. So add-on bit has been enabled. This a conversion rate has going to be started. So it's still normal. Once the conversion has been happened, this is analog. Okay, analog to digital conversion. Here the digital conversion has been, for example, I'm just getting like 450. So the resolution value of 0 to 4095. Since it is having a 12-bit ADC. I got the one conversion. The next conversion value, 1000. I'm just increasing the 1000. So the conversion has been started. Okay. Once the conversion has been started, just getting conversion and next conversion. Okay. So this EOC. So next EOC means the conversion has been ended or not. So here the conversion has been started. Here the conversion is going to be ended. Okay, the ADC conversion is going to be ended. The final conversion is going to be stored into your data register. Okay, the final conversion is actually going to store into your data register. You can check the block diagram also. Okay, so you can able to clearly understand the concepts. So this is how it is actually going to be looked at. So the data is going to be stored in this one. So it's a left aligned, it is a right aligned. Okay. So you will have the lot of contents in this one. So if when you're going to be read it by every specific concept one by one, then only you can able to understand it. Okay. So say for your timers. Okay. So I'm just simply telling you what you're going to be read and the procedures how you can able to given. So just open up and they have been given the first thing. So what timer is not available, you're not going to be used that. And the interaction part, I already told you they have been given what bit of timer, what bit of ADC, and what are the registers and what are the modes it is actually going to be. Okay, in GPIO we saw input mode, output mode, analog mode, alternative mode. So likewise, while you need to do this PWM, so input capture mode, output capture PWM, so and all they have been given. Okay, so yes, it is clock control. It can also taking a pre-scalar use and all they have been given. So in this main features, they have been given the bits. Okay, so what are the modes it is actually going to be performing? Now you will got an idea. Input capture, multiple modes it is going to be. So this is the complete timer configuration. So what is actually going to be? So first of all, just taking a clock. And this clock is going to be divided by the pre-scalar value, and it start to be started by this if you are going to be enabling this value, started to count, the value is going to be loaded here. Okay, so this is how it is actually going to be working. The input clock is going to be coming. For example, I'm just getting a 16 megahertz. I don't want the 16 megahertz. I need to be convert for 1000 only. Simply, I'm going to be divided with 16,000. That is a pre-scalar value of 16,000. Final value of 1000 is going to be loaded here. So it is going to be taken as a 999. Okay, it started to count from 0 to 999. So once you enable this CNT, it started to count from 0 to 999. So it is actually repeating the count. So it is going to be repeatedly going to be happens. Okay, so this is what the thing it is. Okay, it's can able to configuring with the multiple channel. So how can I get the data? So you can read the functional description, what register you are going to be use and what is the purpose of this. And here, since it is having the different modes of data, we can able to check the different registers. Okay, you can able to read the procedure itself. Okay, you can able to read the procedures and all. Yeah. So in this data register, so for each and every pre-scalar value, counter value, so what are the registers you can able to use it for counter mode, so up counting mode. So this is how it is going to be working. And okay, this is the timing diagram of this one. And the clock selection. Okay, how you can able to selecting the clocks. This is the procedure for to do this. So I told you that we are having a different selection. Okay. Like input capture mode. For example, if you are going to be work with the input capture mode, input you are going to be captured. This is the procedure you have to be implemented. Up to six procedure they have been given. For example, if you want to be work on this PWM only, that is timer 9 only going to configure this PWM. For that procedure, yeah, these are the procedure. Only thing is you just go to that register name and setting the specific bit. Okay, so that thing you are going to be enabling. Okay, so see, I want capturing the PWM. So forced one. Okay, forced output capture mode. You can able to use this. This is other procedure. So the output capture mode, you have to be use this procedure. Okay. So for each and everything, guys, now I can't even explain what the procedure is going to be doing. Just simply telling you, if you're going to be work with the PWM mode, you have to inside this timer. They have been given the specific procedure to how to configure this. If you're not understand this concept, you can read it from here. Okay. Output capture mode, how it is if you are sending one data. Okay. So write the register like this. Okay. So this is you have to be enable the C and D. Okay. And then in this CCR1 register, it is going to be sending a data. So while you're going to be reading each and everything, then only you can understand what it is actually sending. So counter register, it started to be counted and we are having these registers going to be enabled. Okay. So these are the things which you are going to be doing. Okay. And this is the pulse actually going to be happening. This is the one pulse mode. Okay. So the CCR1, AR2 reload and value, this is a pulse. So 102, it is counted for 999. So after it just reached this value, again it start to be counted for this another pulse. This is 999. So again it's going to be reaches this another one. Okay. Likewise, if you want to be configure for the different applications, you can able to use it the timer. Okay. And based on the application which you want. So likewise, same for RTC. Okay. So in this RTC, if you want to be write the code, so like if you want to be initializing the RTC. Okay. So the real-time clock, it can possible 32-bit register. So inside this RTC, it is a 32-bit register. So what you can call configure 32-bit register contains seconds, minutes, hours. So this is the RTC. I'm having a time is 11:42 of date. So you can able to set the time as well as date we contain. So the calendar also you can mark it. That is the RTC. So the data which you are getting. So with with the timing, with the date you want to be get, you can configure the timing and day, timing and dates and all in this way. Okay. For that, what we have to be used, so how, what is the procedure, what are the features which is actually add on. Okay. And what are the alternative function outputs? You have to be configuring an alternative function output. And registers, what might be, you can use it inside this. They have been given here. Okay. So after that, you just read the procedure step by step. Okay. So you have to be read the procedure step by step. So if you want to be initialization, the RTC. So these are the procedure you have to be do. So RTC, write protection. So this is the one. So if you want to be calendar initialization, like calendar means like today date is 29/11/2025. So this is the procedure. First of all, just go to the ISR register and initialize it with as one. And then you just go to the ISR and initialize this bit and setting the clock frequency. This is the procedure for calendar. Okay. And then programming for alarm. So if you want to be setting the alarm, so this is the procedure for this. So wake up timer, this is the procedure. Okay. And calendar reading, because that is writing. You are going to be initializing the data. Here, once it has been set, how to read the data with help of this signal. Reset the RTC, because I can do like if I want to be change the time, I'm just simply go to the time clock and time. In this one, I can able to change my time. Okay, here I can, for example, I just do like I want to change the date and okay. This- Here I can able to see the date and time settings. So I can simply do this, guys. So you know this. So if I want to change the date and time, I'm just simply go to this one and date and time. I can easily change my date and time. Okay. If I want to reset it, I can also reset it. If I want to be change the date and time, I can change it. If I want to read it, I can read it from here. So same thing when I want to implement it in your microcontroller by using a program base. Okay, I'm going to be write a program for to writing for resetting the codes. So everything by using the procedure. So I can't explain guys everything by you have to use this procedure. So while doing hands-on only you can understand. So these are the procedure we have. Now I'm just telling procedure is very important. You can take it from here. Okay, so you can able to get the procedures of it. So likewise, for all the peripherals, if you are using a UART, if you're using SPI, if you're using STIO, USB, so everything if you want to be configure, so likewise, everything is holding the same. So if you're taking a transmit or receiving the data, we know that we worked on this UART already, right? So in this UART introduction part, they have been given what are the things it is possible. So what are the register you're going to be used? So features, you just study it, very, very important. And then functional things. So what are the functional display? Transmitting, receiving, stop mode, receiving mode. And this is the block diagram of the register. So while you're seeing the block diagram itself, it is completely giving what are the register which is actually present in the UART. Okay, if I'm seeing a ADC functional diagram, okay, while seeing the block diagrams and all, you can easily understand what are the register actually present inside the micro specific peripheral. So if you see the controller, inside this controller, this is the peripheral which is present. By seeing this block diagram data, likewise, if you are seeing, if you want to be see the block diagram of each peripheral, because I just only see the UART on here. But I can't see the what are the register which is actually present inside this UART. Here, just telling you can configure the SM cards and IRDA. So here, while seeing this one, so here also there. So hardware flow control and normal TX and RX is possible. So while you're seeing the registers and all, so these are the registers are presented inside this UART by configuring by enabling and disabling the peripheral, I can use this here. Okay. So they are also given the character description. If you want to be data, if you want to be sent in character, what is the flow? Start bit, data bit, parity bit, and stop bit. Okay, in transmitter, because if you want to be sent one character, first of all, you're trying to transmitter. This is a procedure. Okay, character transmission, they have been given. So this is the procedure for transmitting one character. A procedure, you just follow the character. Okay, so in the CR1 register, enabling the bit. And if you want to be set the word length, you have to be enabling this one. Stop it, you can do this. Like this. If you want to do the receiver, receiving the data, they have been given the procedure to receiving the data. Okay, likewise. So you are have to be sending and receiving the data is holding the each which is having a different one. So likewise, it is going to be used for the SPI. If you are going to be do the SPI function features, and this is the internal block diagram of SPI. I already told you shift registers, MOSI, MISO, clock and NSSS. So address and bus data is going to be transmitted. Okay. So this is the procedure for each and everything. Okay. Configuring SPI slave mode. This is the procedure. Okay. You have to be set and disabling these pins. Okay. So just to practice, guys, just if after complete this one, just take one SPI and practice how to by reading this reference manual, just to do by the procedure. Okay. So just do by this procedure and try to get it. Configuring master mode. This is the procedure you have to be implement. Okay. You have to be set to the baud rate, and then you have to be set up clock polarity and clock phase and DFF bit. So data format you have to be set. So all the things which you are going to be read it from this reference one. Same for I2C and USB. All okay. I hope you got clear. So if you just go to this I2C, so I2C features, functional descriptions, and slave mode. So because you just read all the stuff, block diagram. Okay. So I2C master control. If you want to transmitting the data, so all must be having the procedure. So transmitting the receiving the data. So having the different procedure you have to be followed. Okay. How you got clear this point, guys? If you got clear this point, you just post the message called as unclear. Okay. Got clear. So for I2C, we'll have this one transmitting and receiving the data. You are going to be using the different registers. Okay. Not only this register, you have to be using the multiple registers. So you have to be studying. Well, because it's not everything is not by the not by like if you are studying I2C data frame. So yes, it is going to be happen by this. So in this I2C data frame, start. What we are going to be studying start data bit, acknowledgement bit. Data you are going to be set. Okay, this is address. Okay, address by set acknowledgement data and acknowledgement and stop. This is the data frame. Okay, by only studying this reference manual, by using this one, because not easy. If you are setting a data bit, yeah, it will be having the multiple procedure. Size you have to be mentioned. What is the data size that we use? Whether it is a word, single character. So based on different procedure, you have to be follow the every single step they have been given. Okay. And a time you have to be mentioned. For that, you have to use the different register. Okay. So if you want to use a time, it is having a different register. Speed, if you are having a different register. So, and type of GPIO, it is having a different. So by studying only the reference manual, you will get the complete detail of this one. So I just provided the reference manual on the chat box. Today you just work on this, just study it guys and try to write a code. Okay, so try to do some project based on this.